Good afternoon, everyone. Thanks for attending the session on a Friday afternoon. I'm delighted to see the audience here. Before I just get started, I had a workshop, and I'd like to see a show of hands. How many of you attended my workshop earlier this week? Oh, great, great. So yeah, for those of you who are not aware, I gave a workshop, so they know a lot about how Cognitive Toolkit works for various text processing tasks, and they're experts at it now, but they don't know the details of what the toolkit is. Okay, so what are the distinguishing features? How does it fare with other toolkits, and where these toolkits are being used? Okay, so you get to hear the front part of the story. They have really mastered the usage of the toolkit. So it really makes it very complementary, these two components. And for those of you who are not familiar with the tutorials and hands-on part, towards the end of the talk today, you will get to see where the code is, and these are self-paced tutorials that you'll get to play around. All right, we'll get started. My name is Sayan Pathak. I am Principal Machine Learning Scientist with the Cognitive Toolkit team. My co-author, Chris Basaglu, sitting in the audience here, is a partner dev manager with the team. And we are going to talk about deep learning. And we are going to talk about building deep models. Before I get to that, I'm sure you are quite interested on how this toolkit is currently being used within Microsoft. Many of you have heard about Microsoft Cognitive Services, and where different kinds of models are being built. I have a slide right after this one that walks you through the different aspects of deep learning that comes into play in building these services. Skype translator, language understanding and language modeling speech is one of the key aspects of these, key aspect of the toolkit. And Skype translator, being a communication platform, allows for a rich bed of innovation and build different kinds of very advanced models. Cortana uses the toolkit for different kinds of acoustic modeling. Bing and Bing Ads, you'll see shortly how we use the toolkit in that area. HoloLens uses CNTK, and Microsoft Research brings in a lot of innovation into this toolkit. Some of these innovations are key differentiators that you will find existing only in this toolkit as compared to the other toolkits out there. So by the end of the hour, you will know all about these. Let's talk a little bit about cognitive services. In vision, as we all know, that deep learning has revolutionized computer vision, and cognitive services definitely benefits from that. There is emotion, face detection. All these things are very conveniently done using CNTK. The code that we will have at your disposal, at least you would know where to find it, empowers all of these kind of very advanced modeling. Speech. This toolkit came from the speech group. So you'll see a couple of applications where speech is used. Language, knowledge, and search, all of these benefit from deep learning technologies. And many of them are powered by CNTK. Many of you have seen the how-ol.net. If you haven't, I recommend that you try it out and have your kids play with it. It really exemplifies the fact that deep learning has come a long way. When it started, the ability to detect the faces here and the corresponding ages was rather wobbly, right? But that's what we all started with our wobbly feet. If you remember, or you may not remember, but your parents definitely do. So when you throw more data at it, here, it gradually trains itself, okay? And that's so very true for deep learning. You start with a certain set of models, you have your data and your task in your hand, you give them exemplary sets, and constantly refine that model. And increasingly, what we are finding is that our models get deeper, bigger, more and more advanced, and along with that comes the need to scalable platform. You need to have a platform that can take that data in and build these very advanced models for delivering realistic applications, so that it won't be a teenager driving a car, but really a well-trained and qualified driver when that driver is on the street driving along. Okay? So the word scalability will come as we go through this talk, and it becomes very, very important. Caption bot, if you haven't tried out, give it a spin. And the captions that come out are really, really funny sometimes, and sometimes it like dead serious, spot on here. So like here, if you see there's a bunch of kids, and it's not only able to say that what the kids are talking about, how their emotions are, but it also has a notion of confidence built in. This becomes important. I'll highlight it in an application just in a bit. Microsoft partnered with this refrigerator company to build a smart refrigerator where you can identify different things within the refrigerator, where they are and what they are. If you wanted to try this kind of things out, there's a tutorial that is available to you. You can easily try it out at your leisure if you chose to. Takes about probably for you to get set up however long you take to set up, but then the tutorial is pretty self-paced. It's in our GitHub site. Many of the innovations from Microsoft Research has become the default starting point where the industry is today. For example, ResNet. How many of you have heard ResNet? Residual networks. Yeah. So people doing computer vision, you'll find that residual networks are kind of the starting point for many of the image recognition tasks. This won the ImageNet competition in 2015, and it really brought down the error rates down to 3.5. This year's the ImageNet winner, like 2016's, is a combination of ResNet and the Inception networks, and it brings down the error rate to 3.1. But you can see that we are hitting that area where 3% range error rate is pretty compelling for building very, very realistic use cases. In this case, this model is available to you as a tutorial. We have a CNTK 201 tutorial that you can take a look at it, self-pace yourself, build it yourself. It'll probably take you about, if you have a GPU, you can build it under 30 minutes. If you have a CPU, depends, yeah, probably whole day. And then you can have some coffee, take a nap, all right? But the thing is this, many of these advanced algorithms are becoming very commodity algorithms and available to you for experimentation. Shanghai Changzheng Hospital benefited from one of these applications being built on top of CNTK. Let's see if I can get the video to work. Excuse me.
In China, there are 100 million people with diabetes. Diabetic retinopathy, or DR, is one of the most common complications of...
Oops, sorry. I shouldn't have tried it.
In China, there are 100 million people with diabetes. Diabetic retinopathy, or DR, is one of the most common complications of diabetes. Patients will go blind without proper treatment.
AdDoc DR is very useful and very easy to use. Just upload the photos and it will give the diagnosis.
We leverage our deep learning technologies with a set of open source tools like Linux and Python. Training deep learning models in Azure is very easy.
With support of distributed training feature in Cognitive Toolkit, we can shorten the training time so we can iterate our algorithm quickly.
Azure provides N24 servers, which is GPU server we use a lot. Azure commercial availability ensures our data security as well as our mission critical service level to our customers. every day is a great day because we are saving people's life.
So increasingly, we are finding people using CNTK are leveraging its computing power, its scalability. I'll have some numbers to share with you shortly, which tells you how the toolkit compares against other options you might have. Here's another anonymous ISV partner working with us, is the Azure partner, and they are working on image similarity. So they have different retail images that they used to scrape from the sites like Target, Macy's, and they were mining it using text-based solutions. But now with image-based approach, they can get much more accurate representation of what those image matches should look like. And they have been using CNTK and benefiting from its scalability as well. Now the toolkit really is designed for production-grade data. It means huge data sets. In this case, being humongous data sets, a diverse range of queries, languages, and data set ranging from video and images equally like. So in this case, you can see that the model learns that most sold fruits in US and automatically tags those fruits in the summarized text that you see here. Now obviously, we haven't built a fruit classifier in this case. The classifier is generic enough and it recognizes different kinds of entities that maps and is able to highlight the summarized text here. There's another application where you generate the summary text from a given set of documents. These are all possible using the toolkit. In Bing Ads, when you serve these ads here, you need to filter them for different kinds of parameters, like whether these images are truly representing what the query is, or even say, a lot of times you don't see it as much, but sometimes you'll see a placeholder image, like a fork and a spoon or image coming soon. Those things are very annoying, and they give you a very poor user experience. So these search engines behind the scene automatically get rid of those things. So many of those applications work at scale, at web scale, and filter these things automatically for you. Now you have seen the translation capabilities that Microsoft brings into its products throughout this conference here at Build. Because you heard it in the keynotes, and you are familiar, if you probably have seen and visited this translate.it, I would highly recommend that you go and explore that capabilities of language translation, where I can speak in a particular language and you can automatically translate that in your phone app that you can install and listen to the content in your native language of preference. You've also seen that in this conference, the PowerPoint plugin got introduced to translate and closed caption the talk that I'm giving. So these are all empowered by DNN models. Behind these models are the strong capability we bring to these products driven by Microsoft research. Earlier last year, this group of researchers from Microsoft achieved human parity in conversational speech recognition. Now there's a very important fact here, which is by reducing this time to train these models, there's huge, huge, huge value that people need to realize when it comes to deep learning. This 5.9 word error rate required a lot of iterations from the researchers. Before using CNTK, they were iterating once every 6 to 8 weeks. With the scalability of the toolkit that comes along, they're able to iterate once every week. Okay? That's a lot of time saved, and you are able to win these challenges because of these scalable things. And as we go into bigger data sets, more and more complex tasks, that aspect of computing becomes more and more important. Microsoft Customer Support Agent, how many of you know about it? Runs on a robot. But very few. It is powered by deep learning. It uses reinforcement learnings and variety of basic deep learning blocks, such as recurrent nets, LSTM, fully connected layers. If these terms don't make sense to you, I'll point you to resources that is available to you for you to quickly learn these things and become familiar. But these are very real technologies delivering real experiences. So this agent actually is able to interact with our customers. So in this case, it greets the customer and is able to parse these naturally formed sentences to extract content that would the relevant content that would help them mitigate their concern. Now, I don't have time to go and explain to you all in details, but large companies are trying these things out. And when they do that, it becomes very important because the bots are very easy to train relative to a diverse range of human population, okay? Besides, they also learn from their previous mistakes. So as they get into the field, they become better and better. how-old.net, yeah. And then they also, the other thing that is very, very important to recognize is that once they are trained, it gets decimated, the whole field, the whole population of bots dealing with the customer calls automatically know what to do with those questions. The bots also know how confident they are, so they can engage the human expert from the relevant field at the right time. This is all empowered by deep learning, and CNTK is a core backbone driving these experiences. Okay. So let's talk about the toolkit. This is an open source deep learning toolkit, and its popularity is rising by the day. It was originally created by speech researchers in 2012. Stands for Computational Network Toolkit, now rebranded as Cognitive Toolkit. On GitHub, it was released since January 2016 under a permissive MIT license. So you can pretty much take the code, build whatever you want to build, and deliver an experience on top of it. We brought Python support in October 2016 in beta, and now we are very close to getting into release mode. We are currently in RC, and you can go ahead and try out the different experiences that we have built on top of this toolkit that is available in open source. We take external contributions, and the number of external contributions are growing. We have strong contributions coming from MIT, Stanford, NVIDIA, and other places that are now increasingly contributing to this toolkit across the globe. Over 80% of Microsoft's internal deep learning load runs on this toolkit. We have first-class support for Linux, and yeah, we do support Windows also. Okay. We have Docker and containers, which makes it really, really easy for you to try out. Python, C++, C#, and Java APIs available. Other languages bindings are coming in as the community is growing and contributions pour in. We do not have any internal code branch. So whatever you want to see, whatever I am working on is in public. So my alias is Sayan, S-A-Y-A-N-P-A. If you are curious what I'm working on, go to the GitHub site and you can look up all the code branches I'm working on. So anybody, it's a completely open development framework. It's fascinating. Many of you ask these questions about how the toolkit performs against other toolkits and why should I explore CNTK versus others. I think every toolkit has a great value tied to it. And as a user, you should be aware of the strengths and weaknesses of each of these. Here is some benchmarking done by our users in Hong Kong University. They use all the toolkits, and they routinely run these benchmarking tests. And you can see I have highlighted CNTK's performance here in red, and they happen to be the lowest also. Okay? Yeah, some of you might be thinking there's a problem with the decimal here. That's not right. This number is right. If you compare our performance on sequences or LSTMs, they really, really show through in stark contrast of the other toolkits, which means that if you're going to build a model using recurrence or LSTMs, you may be saving, it may take a fifth of your time, okay? Or if you're using compute in the cloud, then you may spend 5 times less. Now, we have had this edge on speed for a long time, and we continue to maintain that edge. Back in 2015, when all the popular toolkits that you can see here didn't even have support for multiple GPUs, we had support built in for multiple GPUs. And such scalability is really, really pivotal for large, practical, production-ready, state-of-the-art toolkit that will deliver the accuracy that you expect from today's state-of-the-art methodologies for different applications. There are some really nice experiences bundled with the toolkit in form of tutorials. So here is Jensen, our NVIDIA CEO. NVIDIA is a strong partner from Microsoft. And we have rendered his picture in the style Picasso would have rendered if he were here. Now you can take this code is in the tutorial, CNTK 205, and render yourself or your favorite person in whoever master painter you want that style to be. You can get that experience. It typically takes about 2 to 5 minutes on your whatever computer you may choose, okay? CNTK 205 is the name of the tutorial, okay? And because of the scalability that the toolkit brings, NVIDIA has chosen CNTK as one of the default toolkits in the DGX-1 platform. I don't want you to test your eyesight by trying to read these numbers here, okay, especially those in the back. But you can see that so the gray bars are where the numbers were in August 2016, and this was where it was in November. And you can see that we do focus a lot on compute efficiency and scalability. For this same reason, Cray have built their supercomputer using 1,000 NVIDIA Tesla P100. Some of the experiences that I'm talking about comes from tutorials and examples that you will have at your disposal, and you can really benefit from getting a jump start when you go through the Python APIs and the documentation that comes along with it. So most of the toolkit is implemented in C++, and it's a combination of low-level and high-level Python APIs. There are extensibility features built into the toolkit, which allows to incorporate your own custom user functions and learners in pure Python. And I'll talk a little bit more about distributed readers that are so very important to build your scalable machines that you would like to build today. So let's take a deep dive into the toolkit itself. So CNTK allows you to express arbitrary neural networks by composing simple building blocks into complex networks. I'll pick up a very simple network and walk you through how it is done. The key thing is that as simple or as complex the networks are, they are all production ready, which means you build a network, you should be able to scale it up to your large data set that may not fit in one computer, 2 computers, could be sitting in the cloud. Okay? So let's take a very simple example of handwritten digits recognition from the MNIST data set. It's an optical character recognition task. These are the images, and there are corresponding labels provided by the user here. Okay? And the idea is that given an image that previously the classifier hasn't seen, they should be able to say that this is the digit 6. Okay? This data set has 60,000 training images, 10,000 test images. Each of them are 28 by 28 pixels. I'm going through this for some of you who are very new to the game. I have had spoken to a few of you during the start of the session. So some of these basic stuff that I'm alluding to is available to you through the toolkit, and I'll point to you towards the end of the talk. So let's talk about multi-layer perceptron. This is the basic deep network where you first take the image that I alluded to, a handwritten image, 28 by 28 pixels, and you flatten it into an array of 784 pixels. This becomes your feature. And then you build this layer of neurons or objects where you can do pairwise connection between the output nodes and the input features, and these would define the weights of your network. So neural nets are composed of a bunch of parameters. We call this weights and biases. So in this particular deep layer, you see it has a weight matrix of 784 times 400 and plus 400 bias. Now, if these numbers are somewhat Greek to you, I'll point you to some resources towards the end of my talk, which you can go deeper and find out how they are working out, what the math behind works out like. Now, in deep networks, what you do is you layer these. The input of the next layer takes input of the next layer is the output of the previous layer, right? So the output from this layer becomes the input of the next layer. In this case, I have input is 400, which is the output of the previous layer, and 200 is the number of nodes in the output layer for this layer. And then finally, we want to classify these images into 10 digits, right, 0 to 9. So the output layer has only 10 nodes. Okay? And our model, this red block is going to be called the model. So you remember that, and because we are going to allude to the red block later on in the talk. And these are the parameters we are going to train, these weights and biases. And because there are multiple of these layers stacked on one another, that's why it's called deep models or deep networks. So the output of the final layer is then normalized using a softmax function, and you get a probabilistic interpretation of the input digit. In this case, the digit 3 here is highlighted by the fourth element of the output. So the elements here, the indexes in this array represent the digits such as this. Okay? And we'll figure out how we can train the weights and biases. You're already familiar that given an input image, we can generate the predicted probabilities. And we also have the corresponding labels that you have provided as the part of the training. And these are one-hot encoded, which means that we expand that label set into a length representing the total number of digits in this case. So there's going to be 10 array elements, and the fourth element here representing the digit 3 would be turned 1. This is called one-hot encoding. There's more details in the tutorials that I'll point to later. And you want to build this network such a way that this predicted probability is as close as the one that is labeled. And this is typically done using a loss function. And in this case, we use cross entropy error. There are other losses you can train for. But the idea is that you'll start minimizing the loss. And once you minimize the loss, when the loss is the least, you can imagine that these numbers here would be close to what the label was. That's all about it. So machinery to train that. So now let's see how it looks like in the CNTK side of things. Here are the 3 layers we talked about, the 2 hidden layers and the output layer. W1, W2, and W out are the 3 matrices, weight matrices, and the corresponding biases. And I didn't talk much about the activation functions, but I'll point you to some resources that allude to it. But this is some kind of nonlinear functions which maps the output of this computation in a nonlinear way that mimics somewhat how our brain neurons fire or work. Okay, there's some analogies to it, but there's more to it. I'm just glossing over for sake of time here. Okay, now this is my red block here model, and then we compute the error here. or the loss. So in CNTK world, it's pretty straightforward mapping. In this case, this stands for the Python operator for the matrix multiplication operation here. And it's pretty straightforward one-to-one mapping. So now let's take a slightly deeper dive into what these functions are represented as in CNTK. Here, you'll see that we can break it down into different blocks. X is my input. These are my individual nodes that are functions. And the edges have values. Those are the weights or the parameter values. So this would be whatever is the W1 times X, the value would be, here would be W1 times X. All right? So on and so forth. This becomes, this is my first layer. This would be my second layer, and so on and so forth. So the nodes can be composed of reusable composites. So you could work at this very deep layer, deep level, where you can use primitive functions to combine them together for building higher order models. Or in a bit, I'll point you to something that's the one that you'll see in the tutorials, which takes away a lot of these complexities away from you and makes it really trivial for you to build models. The edges are tensors. They can be sparse, and we do automatic differentiation. This is a bit deeper for those of you who are new to deep learning, but deep learning learns its parameters using backpropagation, which requires you to compute the loss that you computed at the top layer between the predicted value and the one that was provided by the user as a part of the training. That gets propagated and the weights gets adjusted. So that mechanism requires differentiation against the parameters of the network, and we allow automatic differentiation. And this engine also has deferred computation. That means the way the compute structure is structured is you first instantiate the graph, the whole model here, and then the engine automatically optimizes the execution for you. Okay? And you can take the models and clone it, edit it, whatever you want to do at any stage, at any part. Okay? So it does allow you to put things like Legos. Now remember those red blocks and the green blocks? The red block was the model, and the green block was the loss function. So this is what it looks like in the case of this network. So here, the model function has input features, X, and the labels Y. This whole green block takes the X and Y. The model function only takes X, which is the input features. Okay? It doesn't require the label Y. It defines the model structures, and we initialize the parameters. You have to initialize these parameters. Okay? There's 6 of them here. And it holds the parameters that would be learned during the training phase. And the criterion function, which is the loss function, defines the training and the evaluation criteria on top of the model function. I just described the cross entropy function that defined the green block here. Okay? And then it automatically, we do the gradient computation. So in CNTK model, these are all pure functions with special powers that we can compute a gradient with respect to any of its nodes, and we can update the model parameters. Now that we have the small functions, we can create higher order functions on top of it. And you'll see how those higher order functions can be built on top of it if you can combine this matrix multiplication and additions to form composite functions. So a function can be composed to higher order functions by combining them together. And that's exactly what we allow, and this is called layering. There are other higher order functions such as scan, fold, and unfold that help you write very compact representation, that enable you compact representation of the models. So things that would have taken you a lot of code to write in other languages, other toolkits, you can write it in a very compressed way. You can almost take a ruler and measure the length of the code that you write with CNTK versus other. Something that enables that is this layers library. So here you can have dense layers, convolution, dropouts, embedding, and all of these are very powerful functions that are layered on top of these primitive functions. And as a user, you don't need to go to the primitive functions. You can just use the combination of these layered elements. So let's talk a little bit about the workflow. So we have talked about the network model so far. So we want to talk a little bit about the reader and some differentiating aspects of the trainer. So one of the things, before I get to the individual aspects of the reader, where I'm going to talk a bit about the task-specific deserializers, automatic randomization, and distributed reading, let me walk you through the 3 easy steps in which you will find the CNTK recipes are there. So first you read, you create the reader, then you create this red box, the model function, then the green box, the loss function, called the criterion function, then you call the train, and then you run evaluate. These are the steps. Pretty straightforward. Now the first thing you need to do to train your model is to feed the engine data. And when you are going to feed the data, the way you would do it, you would need to randomize your data and feed random samples to your model, small chunks at a time, and you update the weight parameters. That's how the learning happens. So what you need to do is prepare the data, configure your reader network learner, and then call your, say, Python blah.py, which is your script. Okay? So let's see why readers are so important and where the distributed readers and the scalable readers that CNTK has really helps. So for instance, if you have a data sitting in large amount of data sitting in drives that are not, you cannot copy all of it into memory, and you have to randomize that data set, that can be a task in itself. So the way it is done here is you just put this field to be true, and behind the scene, the toolkit takes care of all the randomization for you. Even if the data sits in multiple places in different computers, you can map the network drives to point to those directories, multiple of those, and the toolkit readers will automatically randomize the data for you. This can be a huge time savings. If you're doing image-related tasks, you would like to do data augmentation, so you do different kinds of transformations. So in this case, we are doing some random transformation, random cropping, sorry. You add some jitters, and you are doing some scaling. All of these is added as a transform into your reader. In this case, the image deserializer will automatically read the data from your data set, do all these transformations for you, and then send the data directly to the trainer. This helps to scale the model building process a lot. It saves a lot of time and effort. So it allows on-the-fly randomization for very large data sets, and you can compose different things, like you can combine the image and the text readers one with the other. Many of you in my tutorial session had asked me about the distributed, how you distribute these things. It's pretty straightforward. You can just do MPI exec, and you can point to the number of different computers that you want to run this training on, and then you point to the Python script. Because the readers and stuff are already distributed, they already know where to get the data from, they'll automatically do the job for you in distributing the task of training the model across these multiple computers. Couldn't be easier. And then you can deploy these models in apply to from files, or you can use our C++ APIs or C# Java APIs to run your trained model on a service or a system that you might have. What are the things that differentiates this toolkit with others? So we'll not have time to go through all of them, but I'll do my best in explaining to you these 3 things. First is symbolic loops over sequences with dynamic scheduling. This may sound like a lot of words, but by the time I get done with the slides, it will be very easy for you to make sense what I'm talking. And then we'll also talk about turn graph into parallel program through mini batching. What does this mean? And then the last one I think is the linguistically easier to understand is unique parallel training algorithms. So we have so far looked into the X, which was, say, the MNIST data image, the image data, sorry, which was a flat array of 784 pixels. Now, that's not always the case. That's like that an image doesn't change over time, or it's kind of, the dimension doesn't change either. So in this case, what we do when you are dealing with sequences, say you have a time series or you have a sentence, the number of words in the sentences can be different, or the time series can have different time snapshots, in which case you need to model those time snapshots or the sense of time or the position of a word in a sentence into your model. So the way you would like to do is add a notion of time here. So in this case, if I have word 1, word 2, word 3, so this, say, is time t. This would be, say, word 1 would be represented as time t minus 1, and word 3 would be represented as time t plus 1. Now, you can well understand if I knew what word was preceding this word that I'm currently looking at, it can be hugely beneficial in order for me to do whatever modeling task we want to do. In other toolkits, you will have to do this mechanism. You have to write quite a bit of elaborate code. In CNTK, because it was done with these things in mind from the day one, because speech data, remember this toolkit was designed by speech researchers, so they're dealing with time sequences all the time. So they added this mechanism to really incorporate the notion of time very effectively. In this case, you can simply add a previous state into your model pretty conveniently, and in code, it becomes easier to read. What it shows here is that in addition to looking at the current word represented by X here, this is my word 1, I also want to look into its past value. What was the previous word that was given to me in this particular training? As simple as calling the past value function. If you want to look into the word ahead, you can just replace this with future value. Okay? And then the rest of it doesn't change. So in terms of our graphical layout, what it means is that you are adding a notion of time here, and you're introducing a notion of delay. For those of you who know from signal processing side of things, Z notation, Z transforms often represent delays. And in this case, this past value is incorporated into the graph structure in a rather intuitive way. Now notice that we have introduced a notion of cycle here, right? So whenever graphs have cycle, you have to be, it becomes non-trivial if the toolkit can not fundamentally deal with these cycles in the graph. CNTK is plumbed in, the architecturally supports cycles in the graph, which is very, very powerful. And the toolkit automatically unrolls these graphs. If you have these graph, obviously if you want to look into the future value or the past value, and you have to be able to get access to the different parameters from those states, you have to be able to do something which is called unrolling of the graph. And this is made possible automatically by the toolkit and makes it very efficient and composable. You don't have to do any of that, by the way. The toolkit behind the scene does it for you. You just feed the sentence. You just think, those who did the lab could see that. You design the network pretending that you are working on one word, but you incorporate the knowledge that you wanted to look into the previous word or the following word, and the network automatically did all of that for you. CNTK 202 is the tutorial that we did that day. For those of you who are not familiar and want to do it on your own, want to see what I'm saying as it manifests in those tutorials. The next one is very, very powerful, which is batch sequence scheduling of variable length sequences. So if you have a data set of, say, different queries that you ask, that you type in a web search engine, it could have sentences of varying lengths. One could be 10 words, one could be 2 words. So it could be like, I love sushi in Hong Kong, or I can say, I love sushi when it is bright and sunny, or whatever. All of these can be your sequence data, each of them being one of the sequences. So what you would do typically is you'd start, and this would be your, like, I love sushi in Hong Kong when it's sunny and whatnot, right? Rather long. Then your next one would be I love sushi, and the third one is I love sushi in Hong Kong. So in order to build a network, in most of the toolkits, what you would do is you would take this and you'll define the largest possible word that you'd expect, the largest possible sentence you'd expect, and then compose them as a mini batch or the sequences and fill this with some garbage stuff. Well, don't care values, some random stuff. In this toolkit, what we do is we move things around behind the scenes. We compact the sequences that you're given so that we don't waste any spaces. And we continue to do so. And finally, you are left with only very little space that is wasted. This is called padding. Okay? Now you can imagine not only did we save space, the data access becomes a lot more compact in memory, and you can get potentially huge speed ups. Okay? I'm going to quickly talk about the last part of the last unique feature that I'm going to talk about this session is the data parallel training. So whenever you have a network to train, typically you take a sample from your training set, test set, whatever. And, sorry, not test set, training set, right? What am I talking? So you take a small subset of data and you draw that sample. It's called a mini batch. If you had multiple GPUs to work on, what you would do is you split the data into the number of workers. Okay? So in this case, I have 3 GPU cards, so I'll split it into 3 parts and let all of them work on updating the weight parameters, the weight and the bias parameters. And then once they have done with the new updated weights and biases, I would like to aggregate them, which would mean that you'll have to wait until all the computes in these nodes are finished. Now, you cannot say that all of them would be finished at the same time. So there's some delay in waiting. So typically what is done here is that one way to reduce that bottleneck is to allow each node to process each mini batch data in parallel and let them compute sub-mini batch gradients. So this node will compute the mini batch gradients in one particular slice of the data. And the sub-mini batches sub-mini batch gradients that are computed here are then passed around in a systematic order across the different workers, okay? And then aggregated in a algorithmic way, which is, in this case, is the ring algorithm, all right? Now, the idea is that while the processing is going on, while the compute nodes are busy computing the gradients, that you could do the communication between the nodes from the previous computations, this typical double buffering kind of an approach. And if you can balance the two, then the compute overhead versus communication overhead is vastly, vastly reduced. But you cannot imagine, to have all these nodes finish at the same time for the number of nodes and all that stuff, because different mini batches may take a different amount of time to finish, nevertheless. But at least you got rid of the one choke point that we saw in the previous instance. So what could you do in addition to optimizing or balancing the compute time versus the communication time? So one thing you surely can do is communicate less each time. So the way one would do is here, when these gradients are passed, these are in floats, you don't need to send all the 32 bits, all right? What has been shown here is you can pass 1 bit of information and hang on to the residual error. So when you pass only 1 bit, there's been a certain amount of gradients that you're left with, right? So what you can do is you hang on to that error in your current compute node, and when you start the next iteration, you just start with that error to begin with. Now if you continue doing that, you would eventually arrive at the same optimized parameters, or very close to it, but would have reduced the amount of communication overhead between the different worker nodes. Okay? There's a paper here that has the proofs talking about that it's indeed the case. The other thing that you can do, in addition to communicating less each time, is communicate less often. Here comes 2 techniques. One is automatic mini-batch sizing, and the other one is block momentum. So the block momentum, what it does, it chunks the training data into non-overlapping sets. And so you have the data, you chunked it, say 3 parts. And now each of the blocks, you can chunk it further. And then what you would do is, and these are going to be called sub-blocks. So these sub-blocks are then sent to the GPU's workers, and they train the model. They come up with the updated W star and B star weights and biases, and then you aggregate together in an intelligent way, which is outlined in this paper. I'm not going to recap the steps that are outlined in the paper, but you can read it up. It's some kind of a weighted stochastic smoothing that is used, and what it leads to is a huge scale-up. So you can see that by using these optimizations, you can scale up across 64 GPUs in a linear fashion. Now 1 bit and the block momentum can work together, and these optimizations are available to you in the toolkit for you to leverage and reduce your training time. So some of the achievements are the linear speed up without degradation of model quality. It has been used for a wide range of networks. It's a critical differentiator for CNTK, and it's been used in companies like iFlyTech and Alibaba. Okay? I have some resources to point to you. These are very, very important for those of you who want to explore further. This is our GitHub site. You can go to our wiki, and it's a great place to get started. This is the place, setting up of CNTK on your machine here. Pardon me? C#, if you go to the site, you will see it's in there for the eval part. For the prediction part of the model, once you have trained the model, you can run the trained model using APIs of different languages that are made available to you. So we have C# APIs for that. And then there are tutorials, examples here. And you can optionally try out these notebooks on Azure Notebooks portal. I think I have a slide on that. Okay. And once you start using the toolkit, if you have questions, if you need help, please ask us on Stack Overflow. And please add a tag CNTK for us to be able to respond to you quickly. This one is an important one for those of you who are getting started. Many of you are getting started. I know some of you have come and talked with me. The tutorials that we have are very, very important for you to get familiar with the toolkit. These are self-explanatory, and you can has a lot of contents written in it to be able to explore on your own. And here are the list of tutorials here. It ranges all the way from simple logistic regression to language understanding, image understanding. It also has reinforcement learning. It has the adversarial networks, generative adversarial networks. It has transfer learning, all sorts of stuff. And we continuously add things. So if you want to get some things added, please let us know. We'll be very happy to do so. And Azure Notebooks. This is our partners in Azure. They host these notebooks on the Azure VMs. Now you can access these for free with just a Hotmail or Outlook ID. And you can run through these tutorials. Remember, these are running on CPUs. So if you run the convolution nets, do expect to wait for a long time. Okay, but for some of the 100 series stuff, it works pretty fast. It gets you through the academic learning experience pretty quickly without having to install it on your own machine. But before you go to the 200 series tutorial, I do recommend that you install it on your own machine as well. Okay? It's a pip install. We have a course coming up on edX. Many of the concepts that I quickly had to rush through in this short presentation, you'll be able to hear me out, explain it to you with a lot of graphical and mathematical details that go behind these algorithms. This is the web page for our wiki, and I'm going to end my talk here and show you the website so that if people want to poke around, ask questions, I'll be more than happy to do so. So you have, this may be a good place to start. If you have Windows machine and Linux machines, you can get set up pretty well quickly. It has pip installs. For many of you, you are familiar with pip installs. And all the relevant resources are available here. For the tutorials, we can go to the Python pages. Let me quickly take you to the tutorial page here. So here you can see that we have a variety of tutorials explained to you in pretty basic manner to talk to you about the application where these technologies are used, as well as the technology itself, such as the feed-forward network or LSTM-based networks or VGG or residual network that I was talking about. There's language understanding, reinforcement learning, sequence to sequence. This is very important for many of you who want to try out language translations, GANs, and also transfer learning.